In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 5, Plastic Analysis of Bending, Part 3. We have so far considered the elastic plastic analysis of a rectangular cross-sectional beam. Now we are going to examine different cross-sections. As you can see, this one, the cross-section shown here, is not symmetrical like the cross-section of rectangular beam. Obviously, it has a symmetry about this axis, but it doesn't have any other axis of symmetry. In here, we have determined G1 and G2 relative to the neutral axis. If the neutral axis is in position, if the neutral axis position or neutral plane position is in here, then the area above the neutral plane has the centroid at G1, and the area below the neutral plane has the centroid at G2. These G1 and G2 could be determined. How could they be determined? If we cut a cardboard or a plate made of steel or any other material, it doesn't matter. If we have a thin sheet of material, and we cut it out according to this shape. We cut out this shape out of the board, okay? And then we balance this shape, okay? Put it on a sharp edge. If we put it on a sharp edge like this line and move the sharp edge up and down until we get a balance, okay, then we have this, we find the position of the neutral plane. What I meant is shown in here. If we cut this cross section on a piece of cardboard or a sheet metal which has a constant cross section, and then view it from the side, we will see this shape, okay? It has a constant thickness. That's the side view. And if we rotate it like this and put it on a knife edge, okay, that's a knife edge, and move this knife edge so that we get a balance like that, you know, the weight of this part is equal to the weight of that part. In fact, the weight of that part is equal to the weight of that part. That would be the neutral axis, the position of the neutral axis. So that's the position of the neutral axis. That's G1, the centroid of the upper area, and G2 is the centroid of the lower area. Now, if all the section becomes plastic under this beam is under bending moment load, and we increase the load such that all the section goes plastic, fully plastic, then this we get here YA1 minus YA2 is equal to 0 because due to force equilibrium. Supposing that the area of this underneath here is A2 and the area on here is A1, and supposing that the upper part A1 is under tension and the lower part is under compression, then in order to have equilibrium, we will have to this, because we will have to have this equation, because Y is equal to yield stress, and we are considering the perfectly plastic material. A1 is the area here, so that's the stress times the area is the force on the top of here, and that's the force on the bottom of here. And these forces, of course, act on G1 and G2, and they must be equal in order to have equilibrium. And also A1 must be equal to A2, otherwise that won't become 0, but y cancels out, so A1 is equal to A2 and is equal to half of the area. So the neutral axis must be somewhere between these two. If we have the position of the neutral axis, then we could find the plastic moment, MP, fully plastic moment. Half y times area of the sheet times G1, G2. This comes from the fact that F1 and F2 act on here, and they are equal to y, so y times this distance divided by 2 gives the and times a gives the moment, okay, because we could see that moment is this force, which is y a1 times this distance, and this distance is half of g1 g2. As we can see that a1 is equal to a2 is a over 2, okay, so y times a over 2 is the force acting on g1 or g2. Therefore that force times the distance gives the couple or the bending moment, okay, so that's why we can get this. So for the difficult shapes we don't have to do a very rigorous analysis. We just need to cut out the cross section on a sheet of metal or a sheet of cardboard, any material, and then balance it to find out where the neutral axis is. So once we find the neutral axis, then we could write down this equation and find the complete plastic bending moment, completely plastic bending moment, okay. Obviously nowadays we could find these neutral axis with softwares like CATIA or other softwares. We could find the line which divides the area into two, so we don't need those cardboards or sheet of metals. Those methods were for the old days when we didn't have this kind of softwares. So simply find out the neutral plane, then you can get this equation and get the total plastic moment or complete plastic moment. Now we can consider some asymmetric bending. What do we mean by asymmetric bending? We mean that fully plastic bending must be considered as asymmetrical whenever the axis of an applied moment is not parallel or perpendicular to an axis of symmetry of the cross section. Okay, usually in the beams that we are considering, the moment or the moment axis is parallel or perpendicular to one of the axis of symmetry for the cross section. So if this is not so, we call it asymmetrical bending, otherwise it is symmetrical. Okay, so we have a shape here which is an arbitrary shape, and for this kind of shape we have determined the centroid of this shape, and the centroid GT and GC are the centroids of the areas relative to this neutral axis. Supposing the neutral axis is here, then GT is the part which is on the tension, and GC is the centroid of the part which is under compression if we apply the bending moment. Then we have this formula if it is completely plastic. Okay, remember that we have to increase the bending moment so that the whole cross section becomes completely plastic. In that case we have this equation, and AT is equal to AC equal to A over 2. Now, it says that the above equation completely determines the position of the neutral axis in a given direction, since they cannot be two parallel area bisectors of a continuous cross-sectional shape. Okay, this is unique, this neutral axis. We can't have two neutral axes parallel to each other dividing this area into two. Okay, we could only have one in one direction. Obviously, in other directions, we could have neutral axes as well. So if the bending moment axis is different to what it is now, we could have a neutral axis that way. Okay, let me just show you here. We could have a neutral axis like that or like that. You know, any of these lines that divide the area into two could be a neutral axis for a certain bending moment axis. Okay, and you can see that these neutral axes do not cross G or do not cross each other at a point. These two at a point, these two at a point, these two, but not all of them at a point. The possible neutral axes of a given cross-section are thus the family of bisectors. In general, they do not all meet in a point. As I just mentioned, these are families of bisectors, bisecting the area, this area. Okay, so all of these are neutral axes. For instance, I can draw many lines, like that, dividing the area into two. For instance, I can draw a line like that. That line also is a bisector. Okay. Now, the net tensile force acts through the centroid GT of AT, and the net compressive force through GC, the centroid of AC. Now, that is the area AC, that's centroid GC, and that's the area AT, and that's the centroid GT. As the areas are equal, the centroid G of the whole section must bisect the line GT GC, because we've taken this area is equal to that area, and these are the centroids of the respective areas, the compression, the area on the compression, and the area on the tension. Then this G must bisect the line GTGC. Okay, if GGT is equal to GGC and equal to R, the magnitude of the fully plastic moment is given by MP is equal to R times A times Y. And then we could say in here that 2R is equal to GCGT and is equal to 2G GT 2G GC. Okay, so the R is this distance, and therefore you can see if we had R, we have A and we have Y, therefore MP is equal to R times A times Y. This R in fact is GTGC divided by 2, as we mentioned in the previous slide. In the previous slide here, I had half of Y times area times G1 G2 divided by, half is in fact G1 G2 divided by 2. So here you can see that I have R times A times Y. Instead of 2R divided by 2, I have R. Okay, and now we have talked about the neutral axis dividing this area. We say that the neutral axis is bisector, and we could say that we could have many bisectors. We could divide this in that direction, in this direction, or any direction. Now, we want to know where the direction of the neutral axis is, because we could have many different neutral axes. So the direction of the axis of MP, bending moment, is perpendicular to GT GC. That's the moment axis. Okay, the moment axis is what axis? Is the axis that the bending moment is taken about it. Okay, so that's the bending moment axis. Therefore, if we take the moment about different axes, then we could have different moment axes. So it says that the plot of the curve traced out by GT and GC as the inclination of the neutral axis is rotated through 180 degrees will be termed the centroidal locus. Now this centroidal locus, in fact, is the locus of these points of GT and GC. For instance, for this moment axis, supposing that the neutral axis is then for this neutral axis, this point and that point there are like GT and GC. Okay, now if we change the neutral axis to there, supposing that is another neutral axis, supposing this area there and that area there are equal, then again some point on here and some point on there are the centroidal points. Maybe if I draw an axis here, it's better. So this is another neutral axis. For this neutral axis, that is GT and that's GC for the two areas which this neutral axis has bisects. But the neutral axis that I have just drawn, this also bisects the area into two. Now we have two different areas now from before. Now this area and that area. So the centroidal center will be here, and for the other one will be somewhere here perhaps. So if I draw another neutral axis like that, then maybe I have the centroidal axis somewhere here and somewhere there. So I can get with different neutral axes like that, like that, like that, so like that. I can get different points for the areas which are divided into two, because each neutral axis bisects, divides the two areas into two equal areas, and each area will have a center, a centroidal point. Okay, therefore if we connect these points together, it goes like this, and then we call this a centroidal locus. Okay, so that's how we get these loci in here, or the locus, the centroidal locus in here. In fact, it is the locus of these points. Now what else? Once found, the centroidal locus gives the value of MP about any axis, the value of R being the distance from G to the loci in a direction perpendicular to the moment axis. As you can see here, R is from this point G to a point on the loci. Which point on the loci? The point which relative to that neutral axis. For instance, for this neutral axis, that is the points on the loci. Because if I move this over here, I get the same point. One point on here, one point there, like that. GT and GC. So depending on the neutral axis and the moment axis, then I get different points on the loci. And if I connect G to that point, I get R, and I can write down the total plastic moment for the cross-sectional area. As you can see again here, I have shown this cross-sectional area which does not have any axis of symmetry. So that G, supposing is the centroid of this area, and this line is the loci of the neutral axis. Okay. Now that is the moment axis. That is the radius for the moment axis 1, and this is the neutral axis. Okay. So I haven't mentioned that what is the relationship between this neutral axis 1 and moment axis 1. What is the relationship between them? We knew that neutral axis divides this area into two. That's tension and that's compression. And we know that that point on the centroidal locus is the point or the centroid for the area in here. That area in here, that is its centroid. And that area under the neutral axis is somewhere in here. Okay, that's the centroid. So we know the relationship of R1 to the neutral axis, because once we have the neutral axis, we could find out that point. That point is the centroid of that area. But what is the relationship of this moment axis and neutral axis? Obviously, we know that the moment axis must be perpendicular to this R1. Why must it be perpendicular to R1? We know that the force is acting on the centroid, okay, for this area, which is supposedly in tension. The force is acting on the centroid of this area, which is that point, and when we want to take moment about the centroid, or we want to take the couple about this point and that point, the moment axis is perpendicular to that distance, okay? Because moment is the force times radius, and that is the radius in here, okay? So that must be perpendicular to the radius, because that's the moment axis. That's why we have taken the moment. So moment is about this moment axis, and this is the neutral axis. So that's the relationship between these different points and lines, okay? Let me just go through it once again. Neutral axis is the line dividing the area into two equal parts for when we have a fully plastic cross-section. Okay, this is for a fully plastic cross-section. Now, so we divide the area into two, then we find the centroid at for one area, which is this one, supposing it is in tension, this area, then that would be the centroid for that area, and if we continue this over here, this will be the centroid for that area. Okay, so these 2 points are the centroids for area in compression and tension. Then if we connect this point and that point, it will go through the centroid of the whole area, and the moment axis is perpendicular to R1. So in this way we find out what is the relationship between the centroids, the neutral axis, the radius, and the moment axis. Okay. And you can see here that the neutral axis does not pass through G. It has a crossing point with the moment axis, but it doesn't mean anything. Okay, it could be anywhere. Now, in this paper, which is by Brown in 1967, Plastic Asymmetrical Bending of Beams, it has been proven that the neutral axis is the area bisector parallel to the tangent of the centroidal locus at the point corresponding to the MP value. It says that if you draw a tangent at this point, tangent to what? To this locus. Note that this tangent is not perpendicular to R1 clearly, because we don't have a circle in here. In fact, the tangent is perpendicular to the radius of curvature of the loci at that point. That is the radius of curvature at that point. So the tangent is perpendicular to that, not that. Okay. So it has been proven in this paper. I will upload this paper. I have this paper. I will upload it for you to have a look at it. That it has been shown that the neutral axis is parallel to the tangent at that point. So looking at this in another way is that if we have that point, which is the centroid of this area, or say that any points on this loci, okay, what are the points on this loci? Are the centroids of the areas. So any points of this loci, if we draw a tangent to that point, then the neutral axis must be parallel to this tangent. So in this way we can find out the direction of the neutral axis as well. So if we have a neutral axis, we know that divides the areas into two, and its direction is parallel to the tangent at the centroidal point. Okay, tangent to the loci. So you have to have the curve for the loci in order to draw the tangent. Now, I just want to have a look at this symmetrical cross-section. Supposing that we have a circular cross-section, okay, then that is R, that is tangent, and that is the neutral axis, okay? And you can see that we could have many R's and many at different angles. See? The bending moment axis changes in here. And therefore we could have many neutral axes, infinitely number of neutral axes, okay? Because it's symmetrical, and you can have bending moments in all directions. And all the neutral axes pass through this point. But in the previous slide here I showed you, you can have different moment axes, infinitely different moment axes, and also infinitely different neutral axes. But none of them go through the same points, different points, and they are not symmetrical. But here it is symmetrical, okay? And you can see that neutral axis, tangent, and also one of the things in here is that the bending moment axis also passes through the axis of symmetry, which is coincides with this neutral axis. But in here, due to asymmetrical nature, the moment axis and the neutral axis are different. So let's have a look at this again. In here we have R1 moment axis 1 and the moment axis 2. Okay, we want to consider this 2. So if you look at moment axis 2, we have the tangent and we have the neutral axis. Okay, and that's moment axis 1, that's moment axis 2, and that's neutral axis 2, and R1 and R2. I said that in the Brown's paper it has been proved that the neutral axis is parallel to the tangent, but tangent at these points. Okay, so if I draw the tangents at these points, and in the limits, these will coincide with each other, and tangent 1 and 2 coincide with each other. It could be regarded as a symmetrical case, like the circular case, because now I have different points with different R1, R2, R3, but for the symmetrical one, R1 and R2 become equal. So it could be also argued that if we go in the limit, these will be equal and the neutral axis will coincide each other, and also moment axis coincide with each other, and the tangent will be parallel to the neutral axis, as was the case for the symmetrical case as well. But if you want mathematical proof, you have to go through this Brown's paper, which I will upload for you later on. This is an isosceles triangle. That means this side is equal to that side, and so we have a height h and base b. Okay, and the neutral axis here we are considering the elastic moment, and we know that the neutral axis is h over 3 distance from the bottom, and me is yb h squared over 24, and that's how the stresses are distributed. Okay, so here for instance we have positive or tensile stresses, here we have negative or compressive stresses. And for the fully plastic area, okay, we have the neutral axis here, and we know that the area on the top and bottom must be equal, so we can find out the distance or the height of the top part relative to the bottom part, and we could find out where G1 and G2 are. Once we find out those, we said that for instance this area times the stress in here, that's the stress, which is y, times the area, and times this distance gives us the fully plastic moment. That is the fully plastic moment, that's the elastic moment. So if we divide this together, m plastic over m elastic, we get 2.34 is a factor. Okay, this factor, what is factor? MP is equal to 2.34 times ME. It means that in the elastic part, for the design especially, if you apply a bending moment to a beam, it must be elastic. You shouldn't exceed the elastic limit. You shouldn't go into the yield for the design problems, because we don't want the part or the structure to be deformed. On the other hand, if it is deformed completely and the section becomes fully plastic, you get MP. So that is the relative relationship between the fully plastic bending moment and fully elastic bending moment. This is somehow shows the capacity cross section to carry out load. Okay, here we are not talking about the material. Here we are talking just about the capacity of the section. So relative amounts of the plastic to elastic. So it doesn't matter what material it is, because we have the relative capacity here. So it shows the capacity of the section to carry out load. The greater this number is, the greater the capacity of this section to carry out load. You may say that ME, it depends on the ME, but it doesn't. It depends on both of them, because when we design structures or parts, sometimes we use the plastic capacity of the material as well. In other words, we exceed the yield limit, we exceed the elastic limit, and we go into the plastic. But we don't go into the fully plastic, because it will deform completely. But we let it be plastic to some extent, so that not whole of the cross section becomes plastic, but parts of it becomes plastic. And in that way, the beam does not change its shape, it's not distorted, it's not deformed. Okay, I will talk about this later on in this chapter.